For decades, electronics have driven technological progress. Moore's law, predicting the doubling of transistor density on integrated circuits every 2 years, has held true. But we are approaching fundamental limits. Electrons, with their inherent limitations in speed and energy efficiency, are holding us back. Enter the optical transistor, a revolutionary concept poised to shatter these barriers and usher in a new era of computing power. Imagine a world where data travels at the speed of light, where computation occurs not with sluggish electrons but with nimble photons. This is the promise of optical transistors. These devices, still in their early stages of development, have the potential to revolutionize computing, communications, and countless other fields. By harnessing the power of light, we can overcome the limitations of electronics and unlock unprecedented levels of performance and efficiency. The transition from electronic to optical computing is not merely an incremental improvement, it's a paradigm shift. Just as the transistor replaced the bulky and inefficient vacuum tube, so too will the optical transistor supplant its electronic counterpart. This transition will be driven by the insatiable demand for faster, more powerful, and more energy-efficient computing devices. Optical transistors, unlike their electronic counterparts, utilize photons, the fundamental particles of light, to perform their magic. Instead of electrical currents flowing through wires, we have light beams traversing optical fibers or waveguides. But how do we build a switch for light? One promising approach uses materials with nonlinear optical properties. Imagine a crystal that changes its transparency depending on the intensity of light shown upon it. A weak control beam can then modulate a much stronger signal beam, effectively acting as a light-based switch. Another method involves manipulating the interaction between light and matter at the nanoscale. By carefully engineering structures smaller than the wavelength of light, we can control the flow of photons with incredible precision. These photonic crystals can guide, trap, and even amplify light, providing the building blocks for optical transistors. These are just two examples of the ingenious ways scientists are working to control light at the quantum level. The field of optical transistors is still in its infancy, with new discoveries and innovations emerging rapidly. As our understanding of light-matter interaction deepens, we can expect even more elegant and efficient designs to emerge. The allure of optical transistors stems from the inherent advantages of photons over electrons. Photons are inherently faster, capable of reaching the ultimate speed limit, the speed of light. This speed translates to faster data transfer rates and computational speeds, breaking the bottlenecks of traditional electronics. Furthermore, photons are more energy efficient than electrons. Electronic devices generate heat due to the resistance encountered by electrons, leading to energy loss and requiring elaborate cooling systems. Photons, on the other hand, can travel through optical fibers with minimal energy loss, paving the way for more energy-efficient computing devices. Optical signals are also immune to electromagnetic interference, a major concern in electronics. This immunity makes optical communication more reliable and less prone to errors, particularly in high-speed applications. Finally, photons can carry more information than electrons. Light can be modulated in multiple dimensions, including amplitude, frequency, and polarization, allowing for greater data density and bandwidth compared to electronic signals. This capacity for parallel processing opens up exciting possibilities for quantum computing and other advanced applications. Section 4. The Shadow of Light. Challenges in optical transistor technology. Despite the immense promise of optical transistors, several challenges hinder their widespread adoption. One significant hurdle is the size of optical components. Manipulating light at the nanoscale is a complex and demanding task. While progress is being made, optical transistors are still orders of magnitude larger than their electronic counterparts, limiting their integration into compact devices. Another challenge lies in the materials used. Developing materials with the desired optical properties, such as high nonlinearity and low losses, is crucial for efficient optical transistors. While researchers are exploring a wide range of materials, including semiconductors, polymers, and metamaterials, finding the ideal candidates remains an active area of research. Integrating optical and electronic components seamlessly poses another significant challenge. For optical transistors to be truly practical, they need to interface efficiently with existing electronic infrastructure. Developing hybrid systems that leverage the strengths of both technologies is essential for realizing the full potential of optical computing. Finally, the cost of manufacturing optical transistors remains a significant barrier. The fabrication processes for these devices are currently complex and expensive, limiting their commercial viability. As research progresses and economies of scale kick in, we can expect the cost to decrease, paving the way for wider adoption. Section 5. A future illuminated applications of optical transistors. Despite these challenges, the potential applications of optical transistors are too significant to ignore. Their impact on various fields is poised to be nothing short of revolutionary. In computing, optical transistors promise to break through the limitations of Moore's law. Optical computers could perform calculations at speeds unimaginable today, accelerating fields like artificial intelligence, drug discovery, and materials science. These computers could tackle complex simulations and data analysis tasks that are currently impossible, leading to breakthroughs in various fields. Communication networks stand to benefit immensely from optical transistors. Imagine high-speed, high-bandwidth networks capable of transmitting vast amounts of data across the globe instantaneously. This capability would revolutionize telecommunications, internet infrastructure, and data centers, enabling seamless streaming, faster downloads, and more responsive online experiences. Optical transistors could also revolutionize sensing and imaging technologies. More sensitive and efficient sensors could be developed for medical diagnostics, environmental monitoring, and industrial applications. High-resolution imaging techniques could lead to breakthroughs in fields like microscopy and astronomy. Section 6. Dawn of a new era. The transformative power of light. The development of optical transistors marks a pivotal moment in technological history. Just as the invention of the transistor ushered in the information age, so too will optical transistors pave the way for a new era of light-based computing and communication. The journey from laboratory curiosity to widespread adoption will be challenging and require overcoming significant technical and economic hurdles. However, the potential rewards are too great to ignore. The transformative power of light-based technologies promises a future where computing is faster, more efficient, and more powerful than ever before. As we delve deeper into the realm of light and unlock its secrets, we are entering a new frontier of scientific exploration and technological innovation. The future is bright, illuminated by the promise of optical transistors and the dawn of a new era in computing.